for 11.2 for March 24th. So here's the vocabulary. The point of tangency is going to be that point where the tangent line intersects the circle. So where it hits the circle, that's the point of tangency. Perpendicular just means it meets at 90 degrees. So this tangent line is going to hit this radius, and it's actually going to be at 90 degrees. So that's going to be your perpendicular later on. And then the tangent segment is going to be just any segment that goes from the point of tangency onto this tangent line. So like, let's say that I had another point here. Let's call it point D. BD, that segment, would be a tangent segment. So that's an example of a tangent segment, like from B to D. If it stops. No arrows, just segment. Okay, so theorem 11.1, it just says that if you have a tangent line, then if you make a radius that goes from the center out to the point of tangency, it's always going to be 90 degrees. So even if it's not drawn in there for you, if they tell you that's a tangent line and that that's a radius, it's going to be perpendicular, which is nice because now you're going to be able to make right triangles out of the examples farther down the page. So like right here, where the B is at, that's going to be a right angle. And you're looking for the radius from B to C or from C to B. So if I call that x, I'd go x squared and 12 squared equals 13 squared. Remember, the hypotenuse is the one across from the right angle, so the hypotenuse is going to be the one by itself. The two legs that touch the right angle, the x and the 12, those are going to be on the same side of the equation. So now that you have your equation in Pythagorean theorem, work it out. So 12 squared is 144. 13 squared is 169. You need to move this 144 across the equal sign. Do the opposite. Be fair. On the left side, the 144s cancel each other out. On the right side, 169 minus 144 is going to be 25. Don't forget you have to square root that. If you're using your phone for your calculator, if you turn your phone sideways, usually it gives you the scientific extra buttons. So with me, I have the calculators that we use in class. So if I square root on here, I'm going to go second x squared and then 25, and I get 5. That means my radius for that problem is going to be 5. The radius is going to go with the 15. And then the 17 is going to be your hypotenuse, goes by itself. 15 squared is 225. 17 squared is 289. You're still going to move it across the equal sign by subtracting. So 289 minus 225, 64. And then just like before, you need to square root it. And if you square root, you find out your radius is going to be 8. So that means BC would be 8. Next problem. So this one, you have to watch out because this hypotenuse is being split into the radius and 8 added together. That means that when you write out your Pythagorean theorem, on the left side you're going to have r squared and 16 squared. And on the right side, the r and the 8 being added together is all getting squared. This goes into Algebra 1. The Algebra 1, we had to do r plus 8 times another r plus 8. And then you have to distribute and combine like terms. So over here on the left side, r squared stays r squared. 16 squared is 256. And over here, r times r squared, r times 8, 8r. Then you're going to get the next term, distribute it, 8 times r, another 8r, and then 8 times 8, 64. So we're going to want to combine like terms in here. 8r and another 8r is going to be 16r. Because here is our equal sign, and we have r squared on both sides. Those cancel. we're going to want to move this 64 to the left so that all of the constants are together. Is 192. Now we need to divide by 16 to get the r by itself. And we find out that the radius is 12. So like number 4, going to be exactly the same as number 3. It's going to be the r squared and the 45 squared stay together. Those are the legs. On the other side, the r and 25, the whole thing is getting squared. So remember, that's going to mean r plus 25 times another r plus 25. On the left side, r squared is r squared. 45 squared is 2025. Over here, r times r squared, r times 25, 25 r, 25 times r, another 25 r, 25 times 25, 625. If you look at it, once again, the r squared cancel because you have them on both sides. You're going to combine these two together, so you have 2025 on the left, and you have 50r plus 625 on the right. You want to move 625 across the equal sign, so subtract it from both sides. That leaves you with 1,400 equal to that 50r. So the last step, divide by 50. And then you find out r is 28. So theorem 11.2 says that if you see that you have a perpendicular mark where that tangent is hitting that radius, then you can trust this is actually a tangent. So right here, if you want to see if this works, you need to find out, is this really a right triangle? And to do that, you use Pythagorean theorem as a test. So you still put the 9 and the 12 together because they're still the legs, and the 15 is still your hypotenuse. But this time all you're doing is checking to see if the left side and the right side are equal to each other. So if the left side adds up to be the same thing as the right side, then that means it works. And then you can show that this is definitely a right angle right there. It's a right triangle. Over here you do the same thing. The 6 and the 8 go together. The 9, treat it like the hypotenuse. On the left side, 36 and 64. On the right side, you have 81. If you add these two together, you get 100. That's not the same as 81. And because it's not the same, then you would say this is not a tangent. Then there's I like to call them the jack-in-the-box problems. If you see that in the directions it tells you that these two segments are both tangent to the circle and they intersect at that one single point, then that means these definitely have to be the same. So like over here, if BC is 15, then DC is also going to be 15. And if CD is 14, then CB is also 14, so you can put 3x plus 5 equal to 14 and then solve it. Subtract 5 from both sides, 3x equals 9, divide by 3 on both sides, and you can find your x. So that works on any of these that look like jack-in-the-box head.